The electric dipole modulus of vector P is equal to QA is placed in the plane of the uniform electric field of intensity vector E. Here theta is the angle between vector P and vector E. We shall assume a light thin rod of length A with charges plus Q and minus Q at its two ends as a symbol of electric dipole as shown in figure. The midpoint of dipole and the origin of the coordinate system coincide at point O. Force Q vector E and minus Q vector E are acting on charges plus Q and minus Q respectively. The resultant of these forces is 0. Hence there is no displacement of dipole. The torque due to the force Q vector E on charge Q vector tau 1 is equal to half vector A into Q vector E. Similarly, the torque on charge minus Q is tau 2 is equal to minus half vector A into minus Q vector E. Therefore, tau 2 is equal to half vector A into Q vector E. From equations, we get the total torque acting on the dipole. Vector tau is equal to vector tau 1 plus vector tau 2. That is equal to half Q into vector A into vector E plus half Q into vector A into vector E. That is equal to Q vector A into vector E. Therefore, tau is equal to vector P into vector E. This torque reduces the angle theta that dipole vector P makes with the field vector E, and finally the dipole takes the position along the direction of the field. This is the normal position of the dipole in the uniform electric field. Work is required to be done against the torque in order to displace a dipole from this normal position to a position making an angle theta with the field. This work is stored as the potential energy in dipole.